Okay, so now we continue with subroutine. Right, so actually a subroutine is a sequence of usually a consecutive instruction that carries out a single specific function or a number of related functions needed by calling a program. So a subroutine can be called from one or more location in a program. So this is example here. So you have a program. Okay, so this is your program, right? So now you call a subroutine. What happen is you go to that subroutine, do the program inside of the subroutine, and then after that, after you finish the subroutine, it will return back to the next instruction after you call your subroutine. So this subroutine here is slightly different from branch or jump, right? In which your branch or jump never come back to the place or the next instruction after the jump happen, right? Everything you call a branch or jump, it will never come back to the place where it's starting to jump. But for the subroutine, once it go to the subroutine, alright. For example here, okay, you call a subroutine. So what happen here? You go to this subroutine here, do all the instruction inside of your subroutine, do the task. After you finish the subroutine task, it will return back or go back to the place or next instruction after we call that subroutine, right? And it will continue to this instruction below here. So why are we going to use the subroutine, right? So in order, the reason why we use a subroutine is to use the same set of instruction sequentially or repeatedly. So when a subroutine is called, okay, this is what happen every time you call a subroutine, alright? So when a subroutine is called, the process first save the address of the instruction just below the call instruction on the stack and then transfer control to that subroutine. So whenever you see the call instruction here, it will go to your subroutine and before I go into this subroutine here, what happen is the micro P or your processor will save the address, all right, of the instruction just below this call instruction to your stack, and after that it's going to this subroutine. Okay, for example lah. Okay, so we are going to see the difference between using a subroutine and without using a subroutine. Okay, so contoh. So we have a contoh here. Sorry. So let's you going to do a LED pattern. Okay, LED pattern sequence in which, alright, so this is your LED. Okay, you have 8 LED that are connected to your port B. Alright, so you have 8 LEDs connected to port B. Okay, so this is the sequence here. So the first sequence, okay, what happened is, okay, since you have 8 LED, so the first LED we denoted as 0, 1, 2, 3, 4, 5, 6, and 7. Okay, for the first sequence, what happened is, all right, this red box here indicate that this LED, these two LED will turn on while the rest of LED will turn off. Okay, so this is the first sequence. All right, so you want to display this one here. Okay, you want to do a what you call a running light sequence. Okay, starting from these two LED, and then the next sequence, these two LED will turn on, the rest will off, and then the next sequence is this one is turned on, off, and next is this one is turned on, and then the rest is turned off. All right, so the delay between first sequence to the second sequence, let's be 250 milliseconds. Okay, so what happened is the first sequence you display this LED here 250 milliseconds. Next followed by the second sequence, another 250 millisecond will be displayed, and etc. until the fourth sequence here. Alright, so what happen is, if you're going to write down your programming, okay, let's say you already initialize your port so that your port become an output. Okay, now what you're going to do is, we want to do the first sequence. Alright, you want to send this, we want to do this first sequence by sending out the data to your B. So how to do that? Okay, so load I R16. Okay, next. Load I R16. We use a binary lah. Okay, easy for us to see. Okay, let's this one here. If you put 0, okay, your LED will turn off. When you put 1, the LED will turn off. So what happen is, we have, for binary, we have a 8-bit data. So there's bit 7, bit 6, 4, 5, 3, 2, we put 0, while 1 and 0 we put 1, because we want to do the first sequence. Okay, then we're going to use the out. Okay, port B. Why port B? Because we want to send out this value here to your port B, because your LED are connected to your port B, and then R16. Okay, so this is the first sequence. Okay, next, what are you going to do? Because you want to display this LED here, how many seconds? 250 milliseconds. Okay, so how to do that? Okay, to do that, right? So now you have, sorry, so I need to rearrange. Okay, so this is, okay, just nice. Right, so next. Okay, next is I'm going to do a delay of 250 seconds. So let's, this instruction here is used to generate a delay of 250 seconds. This R16, R20, so I put 250, 250, and then I decrement R20. Okay, is R20 equal to 1, equal to 0? If not, I go to ulang. Okay, so this is my ulang. Right, so this, what we call here, this, okay, these 3 lines here. Alright, so this one here, this 3 line here is used to generate a delay. Okay, the blue color here is to generate a delay. Okay, so it will generate a delay, generate delays of 100 milliseconds, for example. Right, next sequence is, the second sequence is, I need to send this sequence here to your port P, so that your LED 3 and 2 will turn on while the rest is turned off. So how to do that? So this one here, 1 1 0 0. Okay, so because 2 and 3 turn on, the rest turn off, so I send out to port B, and then I need to generate another 250 millisecond delay. So what happens is here, so I need to copy back this instruction here, right, for my delays. Okay, what about the third sequence? Similar lah. Okay, the third sequence, this is my third sequence. Okay, so this one here, LED 4 and 5 will turn on, while the rest is turn off, and then generate 200 milliseconds delay. And the fourth one also same. Okay, I just copy this one here. Now this value will change to 1100, okay, to make sequence number 4. So bit LED 7 and 6 will turn on, while the rest is turn off, and then we call another delay. Okay, so this is what you are going to write by not using the, okay, this one here, without using subroutine. Okay, so what happened here? Okay, what happened here is, by not using a subroutine, every time you want to generate a delay, you need to write down the instruction for your delay generation. Okay, in which, if looking at this programming here, this programming is not efficient. Why it's not efficient? Because you, okay, you waste too much program memory space in order to generate your delay. You see here, one, two, this three line, this another three line, and three lines. Okay, you waste too much program memory space, okay, in order to generate the same delay, which is 250 millisecond. Okay, so how you going to do uh, with using a, so now the second one here, we're going to write down the program, but in this one here we using a subroutine. Okay, so by using a subroutine, what happen is, first, okay, you write down your program here, okay, to generate the first sequence. So this is the first sequence. You send out to port B, and then, okay, and after that you use a call, okay, delay. So this one here, you can put any neighbors as long as call, okay, you want to call, use the subroutine call delays. Okay, so you can put any labels here. You can use a delays, you can use a delay underscore 250 millisecond, or delay 250, or any name that you want to use, right? So this is the delay subroutines, right, in which here the name here and the name of the subroutine that you want to call must be similar, same. Okay, so this is the subroutine to generate the delay, right? So next, this is the first sequence. What about the second sequence? So the second sequence, okay, you just write down the program. Okay, now instead of, okay, so this one here become 1100 out port P R16, and then you call another delay. Okay, before I forget here, you need another instruction called RET. What is RET? Okay, later we will see what is the RET do. Okay, so this is RET. Okay, and this is the second sequence. What about the third sequence? Similar. Okay. Now this one will turn on, the rest will turn off, and the last sequence, the fourth sequence here, is turned on while this is turned off. Okay, you see here. So this is the program without a so this is with a subroutine, right? So compared to this one, this is without a subroutine. See how many lines that you waste in your program memory in order to generate this delay here without using a subroutine. compared to this one. Yeah, in which your programming more shorter and lagi cantik compared to without a subroutine. That's why we are going to need a subroutine. Okay, to use the same instruction over and over again by using the subroutine. Right? So in the subroutine, we have two instructions that you are going to use. For the first one is a call instruction. Okay, so this call instruction is used to go to your subroutine. Okay, right? So call is a long call to subroutine. It call to a subroutine within the entire program memory. So the return address, okay, the which is to the instruction after the call subroutine will be stored onto the stack. So this is the syntax, okay, and operands. Okay, for example here, you have okay move R16, R10, and then suddenly you have a call check means that you're going to go to subroutine name check. Okay, so you go to here, check, do these things here, and after that, every time you see the RET, it will go back to this the the next instruction after you call that subroutine, right? And then the second instruction in the subroutine, we call it as a RET instruction, all right? In which when the execution of the function is finished, okay, the RET instruction at the end of the subroutine is executed, right? So the address of the instruction below the call is loaded into program counter, and the instruction below the call instruction is executed. Okay, whenever you okay, last time as I said earlier, whenever you use the call subroutine, what happen is the what we call the address of this instruction, the next instruction after the call instruction will be stored to your stacks. Okay, and then it go to the subroutine, do the instruction all the time inside of the subroutine, and then whenever after okay you execute the RET instruction, what happen is the processor will take back the address that you store on that you store at that stacks. Okay, load back to your program counter. So now your program counter know that okay, now we need to continue to this instruction here. Okay, which is the next instruction after you call your subroutine. Okay, and then it will do this instruction until the end of your main program. Okay, so this is your RET instruction. Okay, RET stands for return from subroutine. The return address is loaded from the stack. So this is the syntax RET. Okay, example here. Okay, the similar example we seen earlier. Okay, move. Okay, call check. So it will go to this check here. Then compare this number here. Branch equal to error, and then RET. What happen is it will go back to do this NOP. Okay, so now we want to learn about what is the role of stack in your subroutine. Alright, so stack is used temporarily to store address when CPU execute your call instruction. In which every time you call you execute a call instruction, what happen is the next address of the next instruction. Okay, the next instruction will be stored to your stack. Okay, this is how the CPU know where it want to resume when it return from the call subroutine. Hence, we must be very careful when manipulating the stack content. So in order to do that, we need to make sure that our stack pointer is initialized at your RAM end. Okay, so for AVR whose program counter is not longer than 16-bit, the value of the program counter is broken to 2 bytes. All right, so you have low byte and high byte. So lower byte is pushed to the stack first, and then the higher byte is pushed. Okay, So every time you want to take an address, what happen is you store the lower byte first, followed by the higher byte. Okay, but for AVR whose program counter is longer than 60 bit but shorter than 24, then the value of that program counter is broken up into 3 bytes. Okay, you can broken up to 3 bytes. Okay, what happens is the lower byte is pushed first, similar to this one here. You push the lower byte address first, followed by the middle byte is pushed, and finally the highest byte is push. Later we will see how you're going to push your address to your stack. So why we going to use the subroutine? Okay, first is code reuse. You want to use that code over and over again. So we use the subroutine. Easier to understand the code. Why? Because as I mentioned, as we look at the example previously, what happened is the program with and without the subroutine, which one is easy to understand? Of course, with a subroutine, because the program is much shorter compared to program without a subroutine. Okay, so you can do the divide and conquer, which is complex tasks are easier when broken down into the smaller tasks, and to simplify the code debugging process. Of course lah, if your program have less instruction or less programming, it's easier for you to do the decoding part. All right. Next is, all right, instead of the call instruction, we also have the rcall. Okay, this rcall is a relative to call to subroutine. All right, so in which it relative call to an interface for this memory address. The return address, the instruction after the call is stored into the stack. Actually, this is similar to your call instruction. Instead of this one is use a relative call. Similar to jump. Okay, for jump you have jump, rjump, and ijump. Call instruction also have call, rcall, and icall. Okay, so this is for the icall instruction. Okay, so icall instruction is indirect call to subroutine, in which it calls to subroutine the entire memory that specified by your pointer register. Okay, it works the same as the call, but this one here you're going to use the Z to point your call subroutine instruction. Okay, so let's look at this subroutine example. Okay, you are required to write a program to count out from 00 to FF and send the count to port B. Use a call subroutine for sending the data to port B and another one for time delay. Put time delay between each issuing of data to your port B. Alright, so this is the program that you're going to write, and let us see what happens every time you use a call instruction and RET instruction that affected your stacks. Okay, so first include empty2data.inc. Every time you write down your program, you need to include this file here. Alright, as usual. And then the .def count R20. What happened here? Okay, you define your R20 with another name of count. Okay, every time you see the count means that you know that is a R20. Origin 0. What happened here? You want to start your program memory. Okay, starting at address 0. So that's why here you see here. Alright, so this is your program memory. Okay, in which the one that store all this instruction here in your program memory or flash memory. Okay, since your origin with 0, so that's why it started at 0. Okay, so LDI R16 high remain out SPH R16, LDI R16 low remain out SPL R16. You already know that this 4 line of instruction here is used to initialize your stack pointer. Okay, so now what happen here? After this 4 line, okay, after this line here is executed, what happen is All right. Your stack pointer point to address, okay, to your remaining, okay, which is at address 085F. Okay, so this is 085F. Okay, since your stack pointer is 60-bit, so stack pointer need to divide it to high and low lah. Okay, you have the SPH and SPL. Okay, so this is your stack pointer. And then LDI count 0. What happened here? You put 0 to your count. What is your count? R20. Alright. And then C, call display. Okay, so what is call display? Means that you are going to what we call here, you are going to call a subroutine named display. Alright, before you go to this display subroutine, what happened is, okay, now you need to what we call here. Alright, now you need to go to save the address of this instruction here. Okay, so what happened is, okay, the next address after you is execute a call is display is rjam back. Okay, we switch this instruction here is located at address 0007. Okay, so as I mentioned earlier, okay, to store a data to your to store an address to your stack, we need to store the lower byte followed by higher byte. So in this case here, you store 07 and then followed by 00. Okay, so what happened to your stack pointer? Okay, CP stand for your not CP, PC. PC stand for program counter. So now what happened to your stack pointer? Stack pointer will be decremented by 2 lah. Okay, because you have 2 data here stored to your stack. Okay, every time you store data to your stack pointer will be decremented. So now your stack pointer point to what address? 085D. Right, so this is the current value of your stack pointer. Okay, next. Okay, you go to display. Okay, so this is your display, what you call subroutine. Okay, so under this display subroutine, you have this instruction. So in which INC count. Okay, you increment your R20. Out port B count. Okay, what happen is you send out the value from R20 to your port B, and then now you have another call delay. So what happened here? So before you go to your delay subroutine, which is down here, this is your delay subroutine. Before you go to your delay subroutine, what happened is you need to store the next address, okay, after the call instruction, which is this address lah, okay, which is 000C. Okay, you need to store to your stack. Okay, again we store the what we call lower byte first, followed by high byte. Alright, so 000C. Okay, once you store the address of the next instruction, okay, which is 000C, then after that you go to your delay subroutine. So this is your delay subroutine in which you want to generate a certain delay. Okay, load I, R60, OSFF, again, NOP, decrement R60, branch not equal. Okay, if R16 not equal to 0, you keep repeating until R16 equal to 0. What happened here? So now, okay, before that, before I forgot, okay, after, what happened to your stack pointer? So stack pointer now point to what address? Point to this address, right? 085B. So this is your stack pointer. Okay, next, after your decrement R16, after your R16 equal to 0, okay, next what happened is, okay, you see RET instruction. What the RET instruction do? Means that you want to return from subroutine. Return to where? Okay, now you're going to return. Okay, so this address here, okay, will go to your program counter. Okay, 000C. Okay, now your CPU know, oh, now we are going to return to what address? To this address, 000C. That's why now your CPU, okay, return to here. Because last time after we call the delay, okay, this is the next instruction the next instruction after the call instruction, correct? So we need to return to here. Okay, so what happened to your stack pointer? Stack pointer now will be decremented. Okay, and the value. Okay, this one I need to cut. Okay, so it will decremented to here. So now this is a 5D. Okay, so when it go to this 000C, what happens is, oh, another return. Okay, you see here another return. What happens when another return? So what happens is this value here 0007 will be loaded to your program counter. So 0007 loaded to your program counter. What happens to your stack pointer? Stack pointer now will be decremented by 2, okay, which is pointer 005F. And then what happens is, since program counter point to this address, so you need to go to address 0007. So this is 007 and you do this R jump back. Okay, so R jump back equal to this back and call a display. Then what happens when you call this display? So before you go to the display subroutine, so you need to store back this address here to your stack, and this program or this process will keep repeating over and over until it finish. Okay, so this is the subroutine example, and this is what happened to your subroutine. Okay, so this is first you initialize your step pointer. So step pointer will be located at this address, your RAMN. After the call display, okay, is executed, what happen is you store the net address of the address of the next instruction after the call display, okay, to your stack, and the step pointer will be decremented by 2, and then another call instruction is executed, which is call delay. So what happen is the next instruction, okay, after the call delay will be stored to your stack pointer, okay, which is at 000C, and stack pointer will decrement by 2. All right, and then whenever you return from the subroutine, okay, the delay RET, you execute this RET. What happen is you take this value here and send out to your program counter, so that your program counter know that you are going to address 000C, and what happen, your step pointer will decremented by 2, and then this one here another return. So what happen is this 0007 will be to your program counter, and then what happen is the step pointer decremented by 2, and the program counter will go to this address 0007. Okay, this is how the subroutine work by using the call instruction as well as the return instruction.